So, boys started school, and we didn't get all the math videos that we wanted to do over the summer, but I thought there's still a lot of chances to look at just mindsets and thinking ways in how to develop thought processes that help with science and math in your own lives. And what has been on my mind recently is that Einstein once said that if you want your children to grow up to be smart, to read them Undine. If you're not familiar, it's a folk tale, German folk tale about a farmer couple that take in an orphan child, and she ends up being a water spirit, and it's got a lot of the medieval folktale type things of that time, with the night comes in and things going bump in the night. But more along those thoughts, his thought was that teach them to sit and to wonder and to think about things, and how that really comes into perspective is in his own history. He talks about being a child, being on a train, and just seeing how fast he was going. And for some reason, his thought went to the idea of a train going at the same speed as light itself, and what would happen if he had light next to him. And at that time, as a child, he was the one that really changed our perception and our understanding of what light is. But he wondered what would that light look like as he was flying, on the train going super fast, that close to that speed of light. As he looked out, would he be able to see that light and what it looked like? Scientifically speaking, as I start to understand things better, you can't. It wouldn't work. But it got him on that path of thinking and creativity. I remember wondering, what does an atom look like? If you could shrink down to the size of an atom, what would you see? Maybe that was the prospect of my time. The movies, The Incredible Shrinking Woman, and things like that, Ant-Man. But as I've gotten more scientifically minded, the idea of what would you see goes into one of the bigger questions in science is, can you observe something without changing it? And what is an observation? Humans are so visually based that we really base most of what we do with what we observe. There are some psychologists that like to push that we need to be also able to tell a story. And so I've seen myself, I like to develop visual metaphors for everything. A story that I can see and compare it. But going back to what does a single atom or a molecule look like, the problem is that the way our eyes work, light bounces off something, it changes the energy of that light, and that light comes back towards us. We have receptors in our eye that then picks up that light and interprets that in our brain. Again, we have to have some sort of story there, but that comes from some sort of visual input. Or if you're hearing about it, and I don't want to discount the blind have another, some sort of something that comes to them, a sound wave that they interpret. Or if blind and deaf, they have something they feel, tactile, they have to touch it. And along those lines, if you think about a blind deaf person, can they observe a dog without changing that dog? If all they can do is pet the dog, and this is what a dog is that going to change the way the dog feels towards that person? And that becomes a problem when you look at fields like biology. There's an interesting documentary that Disney did, and we can get into the problem with Disney animal documentaries and some of the lies that they perpetrated in the interest of telling a story. But they did one on China, and they were tracking snow leopards through the mountains, and some of the background, they were talking about how hard it was to find snow leopards, and they finally got really good at spotting one, and they followed that snow leopard, and they told that snow leopard story. And it started at the beginning of the documentary. That was the snow leopard that kind of had control of that area of the mountain range, and by the end of it, that snow leopard loses control of the mountain range, and the final shot of the documentary was that snow leopard dying. And the question was, these leopards are so good at staying hidden. They finally found one. They started following it. Were they part of the series of events that because they were observing it, that it could no longer function in that camouflage way that it went through? And the movie itself does not address that. They again, kind of this drone shot of them lifting away from the snow leopard and saying, oh, it's part of the circle of life and it all happens. But as a scientist, I sit and wonder, well, are your drones silent? If you're always following this leopard with this loud drone, is that why that snow leopard is no longer able to hunt? Why other leopards are able to come in and steal her territory? And we don't think about that often, again, because we're so visually focused in our observations as scientists often that we don't. And light, electromagnetic radiation is always bouncing off things. If we just happen to get ourselves in a position where we can intercept what's bouncing off, can we observe something without changing it? And for a lot of biology, it feels like we should be able to do that if we have good blinds and hide. I think there are some people are admitting that maybe not so much. With chemistry, some chemical things, there's some questions about whether or not we can. Because the atoms and the molecules are so small. I guess that's where I started this. Light, as we understand it, has a specific wavelength, and which means the way it moves is interesting. Things that are smaller than that wavelength, the light won't interact with. It will just go straight through them and past them. It won't affect the light. And so my question as a kid, what would an atom look like if I shrunk myself down to that size? It wouldn't have a visual appearance. Now we can look mathematically and look at energy levels, and we can visualize or get visual representations of those mathematical energy levels, and you can get some really cool diagrams of these energy distribution, where the electrons might be. When we did molecular simulations, we talked about vibrational energies, again, your torsional energies, angular vibrations, and all that, and we have some math to represent that. But it doesn't. But in order to really understand that, I have to go back and I have to then make a visual model in my mind and tell myself a story about what's going on with those mathematical numbers. Otherwise, it doesn't make sense. And then going back to Einstein from that, as light wasn't full understood at the time. I think there's still things about light that we don't understand. But he had that question of what would light look like if I was going along. And the question is, well, does it have an appearance? When we talked about our eyes, what we see is light entering our eyes. If we're going the same speed as light and we're on a parallel path as that light isn't entering our eyes. And does it have an appearance really if that light triggering what we represent in our minds as an appearance is what that light does when it touches these receptors at the back of our eyes and then come back into our brain and trigger neurotransmitters that say, this is, we just got an energy packet and these receptors got this energy packet, and so it's going to pop up here and our brain thinks that's a color at that spectrum there. Or if it hits all three of our different types of color receptors, oh, that's white, and that type of thing. But it was good for him to sit and just ask those questions. I think another one that I remember thinking when I was probably about that same age was, could you capture light? Like the idea, if you look in between two mirrors and you see going on into infinity, as you know, as each one further back is a little bit darker, a little bit dimmer because you're losing some of the light going back and forth. What if you had perfect mirrors that reflected 100% of that visible light? What if you then made a box out of those perfect mirrors? And is that the light's moving so fast, because I understood more about light because what Einstein had taught. Uh, could you take a box made of these perfect mirrors in a fully bright environment, directly faced at the sun? You close that box really quick, and then you run down into a really deep, dark cave, and you open that box, where you get a burst of light. Would there be enough that would bounce out, and you could actually get it from your light receptors? Is it moving so fast? What would happen? It was just something that was fun to think about. And then to go, and as I understood light better, to be like, oh, well, that's an energy packet of electromagnetic radiation. Can you carry around electromagnetic radiation? It moves around itself throughout space. I kind of rambling here. I don't remember where I wanted to go. Just some things to think about. What are you doing in your life to foster this imagination? What are you doing in your life to really give yourself time to think about these things? One of the interesting things about Einstein, the time he lived, was called the golden age of physics, because it was a time when people were really making leaps and bounds of increased understanding of our world. And at this time, people have asked, is that dead? Have we hit a stopping point? There's a YouTuber I really like, Sabine Haas. I can't remember her last name exactly. It's a really great German name. She's a fun German person to listen to. But she talks about how ruined our academic institutions are, and the state of science publication, in that I won't go into the details, but the incentives aren't there. But going back to why Einstein's time was really interesting, there were kind of two different sets of scientists at the time, and he admitted that he was of a theoretical type. The other set was the experimental type, and these are just amazing men that were designing experiments, coming up with hypotheses. These experiments were supposed to elucidate ideas that they just had an idea of. We joke around in chemistry a lot. One of the problems with chemistry is that you start with a clear fluid and you mix it with another clear fluid, and those two clear fluids are supposed to be two different things, and you get a third clear fluid that's going to be different than the original two ones. And how do you tell what was what? And so some of the chemists of that time, Millikan and Rutherford, that were doing some amazing things, that came up with crazy ideas to test hypotheses, and then they got different results that then they even expected, and they had to go back and say, well, what does this result come into, what does that mean for this hypothesis? These were the experimental people at the time. Those are the chemists. There were physicists doing your slit experiments. Is light, you hear the term quantum, which means smallest possible piece. Is it a quantum particle thing, object? In which case, they started doing experiments. Can you break this energy level into infinitely small pieces that they're continuously modifying? In which case, light would be more of a wave. And so they'd see that with a slit experiment, where it starts propagating out like a wave, like either a compression wave, or and that gets into gravity too. Anyways, they had all these experiments, and they would see, if I do this experiment, the slit experiment like this, it acts like a wave. But if I then try to do quantum experiments where, okay, I should then get an infinite variation in energy levels, I actually instead get jumps. And if there's jump levels, then I have a smallest piece, and it comes as a packet, and that packet is more particle-like. And so they're doing these experiments. But what Einstein does, he was able to sit and think. He was able to conceptualize things, because he was able to sit and think and come up with mental, really metaphors, ways of thinking about things that then helped understand it. But beyond just sitting and thinking about it, he then developed math equations that would show that. And over and over, the physicists keep saying, well, Einstein was right. These things that the experimental physicists at the time couldn't find ways to experiments that would actually prove these things right. 100 years later, not quite 100 years later, because he was about 1940s, but 80 years later, so we're continually developing new experimental techniques that are proving his theory is correct. And what really helped Einstein to do that, I talk about he was working in a patent office, and yes, he was doing work going through the patents and understanding the patents and whatnot, but then he'd have a lot of downtime in which he could just sit and think about things. And as he was thinking about things, he did the work. People say he wasn't great at math. He actually, it's one of the ones I've heard both on. I think it's more that rumor side that he wasn't good at math, but he went through and he did the mathematical proofs. He's like, okay, I've got this mental model in my mind of how things could work. Can I find mathematical ways to show that? And he went in, so instead of experimental, this theoretical things, he did these math equations and showed all these things. And then, like I said, the experimental physicists have been catching up. But there are questions about, have we hit a limit? And again, I guess the whole point is, are we finding time to sit and debate things and to wonder about things and to understand them in our minds? And I know for me, I hit this point where I need to have something in my ear playing at all times, and just hearing something isn't enough. I've got to put it on 2 to 3 times speed. I got to get it crammed into my head as fast as possible, and I'm not taking that time to stop and think. And if I do come up like, oh, you know what? Compression waves we talk about. One of the big things Einstein was recently proven correctly on was gravitational waves, and you get that thought experiment of gravity is like a big. You get into one of the theories at the time was ether, which was that if in order to have a wave in something, that something has to be made up of some sort of medium or substance, and the idea of ether is it was a non-molecular substance of space. And so then things moving through that substance of space would then cause the forces that we are able to experience. And because we are made up of these energy fields in that substance, we can't actually experience that substance, that us moving. Kind of weird ideas, but that's been mostly disproven. However, since we do have gravitational waves, what is that? One of the ideas then is, what is gravity? And all the way to conceptualize that is, say, curvature in space. And so they put out a sheet, and then they put a ball on that sheet, and you see that sheet, curve down. They grabbed a whiteboard, and you see the idea, like the sheet, and it curves down, and you have the gravity well down at the bottom, and things that orbit around that gravity well are actually going in a straight line, but it's the curvature of the gravity well that causes it to look like it's going around, for us, the curvature of space. The problem is that you're taking a 3-dimensional space and then flattening it to a 2-dimensional area to show that gravity. And the idea is that we are actually in a 3-dimensional space. And so how do you then expand that out? Well, you then have to push that gravity well onto its side and upside down and turn this way and actually have it infinitely surrounding that bulb. And so instead what you're seeing is a compression of all of space around where there's mass, and that's what's causing gravity. That as things start moving towards this compressed space, they slow down. One of the ideas there is, if you think about driving a car, maybe I should think about who this is targeted to. But when I was learning about refractive index, you have a car going down a road, right? And on the side of the road is dirt. And if this car is going down this road, starts to shift over towards the dirt, once they hit that dirt is harder to go fast in. And so the speed here is this fast speed, but the speed here is the slow speed. If you've ever accidentally got off onto a dirt road, what you notice, because this is a slower speed, it's pushing this side forward more than it's pushing this side, and the car naturally turns towards it. And so the idea of that space is compressed around matter, then is what causes that curvature, not necessarily that, because again, in order to understand that curved space, that it's going to go down the gravity well, we have to have a second form of gravity that's pulling something down a hill. But instead, if you actually see that as infinite gravity wells in all different directions, it's just actually a compression of space around mass. That what's happening is, as you get in empty space, the massless space, the space is spread out. You go faster. It's like faster roads. Then you hit this compressed space. It's more dense, like that packed dirt, and you then start to get pulled into it, and that's what's causing that curvature. But having those ideas, and there's some interesting theories out there that then gravity only exists because time exists, and then if you have gravity only existing because time exists, again, where I did a lot of my work with molecular dynamics, and maybe the corollary to this is, if you've ever heard of the game Space Invaders, it started off slow because there's too many things. You had a little spaceship on the bottom and aliens were coming back and forth, and you have to shoot up the aliens. And it started off slow because the processor that was processing that couldn't process all the different aliens at the same time, so it would slow down the simulation. But as you start shooting these aliens, there are fewer for it to process and keep track of, and so it starts speeding up. And the natural consequence was that things would go faster as you get more stressful near the end, making it more enjoyable. But the idea that the more mass you have around something, the slower that would then go, and that then cause a curvature. Then it gets into, well, is all of life a simulation, or is all of space on some computer somewhere? And it's the type of thing I did, where you have these parallel systems that would depend on each other. Some of the ones out where there's fewer molecules or particles, they could process a little faster. And if they were far enough away, they wouldn't have to actually need the computations of the ones that are closer, or that are more packed. And so things could go fly faster, time would fly faster there, but time would slow down for each step where it's more closely packed. And then as you start moving towards that, because it's slowing down, you then start getting this gravity type effect. It becomes an interesting thing if you look at the four fundamental forces, that your three electromagnetic, weak nuclear and strong nuclear are kind of what's being calculated at these different time steps. And then the gravity itself is just the effect, the fourth one that doesn't seem to match or interact with the other ones as much in that. Yeah, it's a crazy theory, and I've never actually sat down and just, what would be the math to try to prove that out? But you get some interesting aspects on that, where when what becomes a black hole, well, it's an overflow. You get whatever node is calculating the interactions for this mass, and there's so much mass there that it times out, and it's forced to move to the next time step. And so you see all the physics stuff that says, well, in a black hole, time stops. So it's because it's never able to finish calculating. And is that what is life a simulation? No, I not very great evidence for it, but it's an interesting way to conceptualize and think about, well, what are these forces throughout the universe that's keeping the solar systems and everything running, and it's just fun. And the question is, how much time do you get to sit and think about these things and delve into them? And it does require some research. It does require getting primers, things to get you started on those paths. But then also it requires time to really digest them, to sit and to think about them. Anyways, that's a not so quick little thing on thinking about stuff. Keep thinking, stay sharp, and have a great day.